Let's now get a pre-trained model. So getting a pre-trained model will freeze the base layers and change the classifier head. So you may have already done this or given it a shot because we covered it in the last section, getting a pre-trained model, but let's now do it together. So I just want to show you the old way of doing things because you might see this in other old PyTorch sort of demos and whatnot. So note, this is how a pre-trained model would be created prior to Torch Vision v0.13. So we would go model equals torchvision.models.efficientNet, let's say efficientNet b0, our old faithful, pre-trained equals true. And then we could send that to the target device if we wanted to. And then if we had a look at the model, it's going to download a model. It's going to work, but it gives us this little warning message. So let's scroll up here. If we go up, yeah, user warning. The parameter pre-trained, which is this, is deprecated since 0.13. There we go. And will be removed in 0.15. Please use weight instead. So let's see what the new version looks like. And just remember, I'm just showing you that because it's good to be aware that this is a pretty major change in terms of how PyTorch pre-trained models are created. So it's good to be aware of how they were created. So download the pre-trained weights for EfficientNet. So this is using the new version, so 0.13 onwards. EfficientNet b0. So we saw this before. Weights equals torchvision.models.efficient, I have to spell these things out, EfficientNet b0 underscore weights dot default. So just a reminder, default equals best available weights. And if we wanted more of them, some models have multiple different types of weights. This is in the documentation. You just have to make sure you're on the version 0.13 onwards. So for me at the moment, this is the nightly version. And then if I go to models and pre-trained weights, classification, we've got a bunch of different model weights here that we could try, each with varying results on ImageNet and each with varying numbers of parameters. So that's where you can find pre-trained models in PyTorch. Don't forget, there's also other places such as the Hugging Face Hub. We have weights equals torchvision.models, EfficientNet b0 weights default, the best available for EfficientNet b0. Now, to create a new model, this is the new way. Set up the model with the pre-trained weights and send it to the target device. So just as we've done above in the line that's commented out, this is how we would create that same model, but using the new API. .models, EfficientNet, b0, and then in here we're going to do weights equals weights, and then we have a look at our model. Beautiful, we get the same model here. So using that weights, and just a little tidbit, make sure this says weights, not weight, because I've been caught out on an error for quite a long time with the wrong parameter name in there. So I'm going to comment that out to save some space. Now, let's freeze all of the base layers in this EfficientNet b0. So if we go have a look, before we freeze them, freeze all base layers by setting their requires grad. So PyTorch, requires grad attribute to false. So PyTorch will automatically behind the scenes track the gradients of our model parameters. And if we wanted to update them and have them better represent our data, our optimizer would update that gradient as our model looks at data. So if we set the requires grad parameter to false, requires grad equals false, it's going to freeze them during training, so they won't have any gradients to track. So let's just print the param. We're going to see quite a few things here. Yeah, there we go. So these are all the pre-trained features that our model comes with. So these are all learned from ImageNet. We've got a whole bunch of different things, all numbers, numericals, numerical patterns, representing what our model has learned on ImageNet. And as we've seen in 0.6 or 0.6, that it turns out that these are actually pretty good patterns in terms of computer vision. So let's comment that out. We'll set all the parameters requires grad to false, and then we will change the classifier head. So we might just do that in the next cell, equals false. Beautiful. And if we inspect our model, so model.classifier, some models will have a different head on them. So if we inspect our model one more time, we've got a few components here. We've got the features component. This is for EfficientNet. We come down, all the way down. Look at all those layers that we get to use. Average pool and classifier. So some models may call this a different name. You just have to be aware of how to inspect it. So for us, it's the classifier head, but the principle is very similar across different model types, is you want to adjust the output layer, whether it's a classifier head or something else, you want to adjust the output layer to suit your own problem. And for us, instead of having 1,000 out features, we want 3. So adjust the classifier head. We want nn.sequential. We're just going to reproduce it just the exact same, but with our number of classes. We want 3. So I'll bring in dropout and p equals 0.2. In place equals true. Just going to copy exactly what's there. And then we'll go nn.linear. The in features is going to be 1280. That's going to be a feature vector of our whatever image is going through the network. And we'll change this to 3 or len class names, which will also be 3. Beautiful. So let's adjust the classifier head. We might also send that to the target device, and we might set the seeds here because this is going to instantiate a linear layer, and behind the scenes, the weights of this layer are going to be initialized randomly. So for as much reproducibility as we can get, we'll set the seeds, we'll send it to the target device because this is a part of our model. And when we downloaded the model, we didn't actually send that to the device either. I've written it there, but maybe I didn't do it. So maybe you caught that error, but we'll just rerun all of those cells. And now we can use torch info to get a summary of our model to check out what's going on. So from torch info, import summary. And so let's get a summary of our model, and we'll put the input size. Let's set this just to a batch of 32. 3 color channels, 224, 224 for height and width. That's going to be our image data. Verbose equals 0. We'll get a big printout. Col names. We can set up some col names here. So we want to see the input size and output size of each of our layers. That's a very important thing to inspect in deep learning models is input and output shapes. We'll check out the number of parameters each layer has, and we'll see whether the layer is trainable or not. And then we'll just set some values here for aesthetics, column width to 20, and row settings. Let's print out the var names. So let's see what this looks like. Wonderful. So this is what we covered in the last section. We've got an EfficientNet, and we've got our features section here, which is comprised of multiple different groups of layers and some activations here. We've got input and output shape of each layer. And you can see our image data gets manipulated as it goes through the network. And each layer has a certain number of parameters. And right now, all of the base layers are frozen, so they won't be updated during training. So we have a feature extractor model here. And we have updated the classifier layer to suit our own problem of only having 3 output units. And so that is the only layer that is trainable. So hopefully training goes pretty quick. As we saw in the previous section, we have just under 4,000 trainable parameters. And if we want to see that in the colored version, we go back to the keynote. Here's what we've got. Torch Vision models EfficientNet B0. Many of our layers are untrainable. In other words, they're frozen. Only our last layers are trainable. And we've updated the final layer to suit our own problem. If you had 10 classes, what would this value be? It would be 10. And now, because we've set a lot of the layers to be untrainable, our trainable parameters is greatly reduced. So therefore, the number of calculations that PyTorch code will have to make behind the scenes is greatly reduced. So training speed is hopefully reduced as well. So let's go back. It's now time to train a model. But this time, instead of tracking our model's results in a dictionary like we have been, we're going to save them to a file. So you might want to have a look. This is if you want to go ahead, a challenge for you is use TensorBoard with PyTorch. If you search that, we've got a tutorial here, beautiful. You might want to go through that and see if you can figure out how to use TensorBoard with the code that we have here. Otherwise, we'll cover that in the next video. I'll see you there.